So the bottom line here is we've been using the quadratic formula for the last several lessons to solve quadratic equations. By now you should be really good at using the quadratic formula. So we can get the exact answers to any quadratic equation we want to just by putting the a, b, and c into the quadratic formula, and we always get the two answers. But it turns out that we can actually learn a lot about the solutions of the quadratic without actually cranking through the entire quadratic formula. In other words, we may not always care about the exact solutions, but sometimes we may want to understand the nature or some characteristics of those solutions without going through the whole entire quadratic formula deal. So in order to understand that, we need to kind of break apart the quadratic formula a little bit and talk about one part of the quadratic formula that we're going to call the discriminant. And based on how that discriminant looks, we can actually learn a lot about the solutions of the quadratic equation without actually cranking through it all. So I want to break out what the quadratic formula is. I'm going to show you what that discriminant is here briefly on the board. And then we're going to go over to the computer where I can show you visually what is happening when that discriminant changes with a graph of a quadratic function. So stick with me to that point and you'll definitely see an awesome little demo of that. So we have generally, any quadratic equation is going to generally look like this. ax squared plus bx plus c is equal to 0. And by now you know that a and b and c can actually be real numbers. They can actually be square roots. They can be rational, irrational numbers. They can also be imaginary numbers. A, b, and c, we've done some problems where they're actually imaginary. But for the purpose of this lesson right now, we're going to just say that a and b and c are real numbers. They can be negative, they can be positive, they can be fractions, they can be radicals, but they're definitely just going to be real. All right, so we know that we can solve this quadratic equation using the quadratic formula, and we're going to get two solutions. The first one, we're going to call it x1. It's going to be negative b plus or minus, actually I'm going to take away that minus for now, negative b plus b squared minus 4 times a times c, the radical goes around this guy, all over 2a. That was solution number one. The only difference between the other solution is this plus changes to a minus. So we're going to call the next solution x sub 2. And it's going to be negative b minus b squared minus 4 times a times c, radical goes around all of this stuff, all divided by 2a. So we have two kind of mirror image solutions. Notice everything is exactly the same, but one has a plus sign and one of them has a minus sign. We've been doing this over and over and over again for many, many, many lessons. So now what I'm trying to tell you is, of course, we can take a and b and c and we can stick it in and get these solutions. But we want to understand some characteristics of the solutions without actually calculating the entire exact answer. So in order to do that, we're going to define something. We're going to say let capital D, we're going to call it the discriminant, but we're going to just let it equal to whatever this stuff is under the radical, b squared minus 4ac. And this is called, this triple thing means it's equal by definition to be what we call the discriminant. Discriminant. So when you really think about it, the reason we're setting it equal, you say, well, why do we set it equal to what this stuff is under the radical? It's because what is under this radical really governs what the solutions of the quadratic formula will be. When you think about it, that radical is the most important part of the whole thing, really. Because if you think about it, if what is under the radical, and I mean, when I say what is under it, I mean the whole thing. If it's a positive number, then you'll be able to take the square root of it and you'll get real answers. But if what is under that radical actually turns out to be negative, then when you take the square root of it, you're going to get imaginary numbers. That means your answers will be imaginary. And if what is under this radical is neither negative nor positive, but actually exactly equal to 0, we have another special case. So we know that what is under this radical is really, really important to tell us what the solutions look like, and we have a special name for that. What is under the radical here is called the discriminant. So any time that you're in an exam or a test or in class or a book you're reading or something that talks about the discriminant, in your mind you need to think that's just what's ever under the radical in the quadratic formula. That's what we call the discriminant. So let me write it down a little bit more explicitly for you. These solutions here that we all know and love, we can rewrite them in terms of the discriminant really easily. So it would be negative b plus the square root of this discriminant d, because it's equal to the whole thing here, over 2a. And the other solution, x2, is going to be negative b minus the square root of this discriminant over 2a. So you see what I mean here? What is under this radical, this special thing we call the discriminant, governs the whole thing. It governs whether the solutions are real numbers, whether the solutions are complex answers. And that's what we mean by when we look at solutions of quadratics, that's the most important thing about the roots is, are they real numbers or are they imaginary numbers? And in a few lessons, I'm going to talk to you in a whole lot more detail about why we even get imaginary roots to begin with. But for now, let's focus on what this discriminant is telling us. So there's really a couple of cases, and what I'm going to do is I'm going to show you what happens when this D here, this discriminant, is different cases. We're going to talk about it. And then we're going to go to the computer where we can graph and see exactly what's really happening here. So we're going to assume here, when we talk about the discriminant here, that A and B and C are real. And what I mean by A, B, and C, I mean the coefficients in front of all the parts of my polynomial, they're real numbers. They can be negative, positive, fractions, decimals, square roots, that's fine. But they can't be I, because it confuses things and clutters things up if you talk about these things up here being imaginary. So for now, let's just assume that they are real numbers. Then we have basically three main cases. The first case is if this discriminant, which means whatever's under the radical in the quadratic formula, is greater than 0. It means it's a positive number. Then what this means is that when I take the square root of a positive number, I'm going to get a positive answer. Right? Square root of 49, square root of 38, I'm going to get some kind of positive answer. I can then add to negative b, divide by this, but no matter what happens, if this discriminant is bigger than 0, I'm going to get a number that's going to be added or subtracted and so on. I'm going to get 2 roots as the answer. They're going to be both real roots, no complex numbers anywhere, and they're going to be unequal. And this should make complete sense because, for instance, if d, we're saying it's positive, let's say d becomes 36. Then I take the square root, I'm going to get a 6. Then I'm going to basically add a negative b and divide by 2a, but a and b are real numbers, so no matter what happens, I will always get a real answer because what came out of this radical was real. Because I'm adding in one case and subtracting in the other case, I'm going to get unequal roots. And of course I'm going to get 2 roots because if I have the same exact thing here, I've got the same thing here. In one case I'm adding this number, and in another case I'm subtracting a number, then the roots are not going to be the same. That's what happens most of the time in the quadratic formula. Whenever you get a positive discriminant, you're going to have 2 roots. One of them is going to be a little bit displaced from the other because it's plus and minus, but they're both going to be real. That's case number 1. Case number 2 is, you might guess, well, what happens if this discriminant actually isn't bigger than 0? What if it's smaller than 0? Then if you think through the logic, let's say it's negative 36 you have under this radical. Then if you take the square root of that, you're going to get 6i because you have a negative number under the radical. You always have to have an I. So because of that, you're still going to have 2 roots, but they're not going to be real anymore because you've introduced an I anytime this discriminant is less than 0. So you're going to have 2 roots, same as before, but they're going to be complex conjugates. And remember, complex conjugates means a complex conjugate is like 1 plus 2i and 1 minus 2i. Or 1 plus 7i, 1 minus 7i. It's the same thing, you just have a negative sign in front of the imaginary part. You switch the sign of the imaginary part. Those are conjugates. So if I have a negative 49 here and a negative 49 here for my d, for my discriminant, when I take the square root of that, I'll have 7i. Then I'll be adding 7i and subtracting 7i. So they'll be complex conjugates because I'm switching the signs of the imaginary parts. I'll still have 2 of them, 2 roots, because in one case I'm adding, in one case I'm subtracting. And that's what happens oftentimes with the quadratic formula. You will get 2 roots that are complex conjugates of each other. Now, the third case is the very special case. What if this discriminant exactly happens to equal 0? What's going to happen there? Well, it can happen because b squared minus 4ac, it's just a calculation based on my polynomial. So if I pick b and a and c perfectly, I can make this thing go to 0, b squared minus 4ac. And if this d becomes 0, then it's negative b plus square root of 0, but that just becomes 0. So it's basically negative b over 2a for the root number 1. And if the discriminant here becomes 0, then it's negative b minus, again, square root of 0, so 0. Negative b minus 0 is nothing. So it's negative b over 2a for this and negative b over 2a for this. So if the discriminant is exactly equal to 0, I have real roots all right because I haven't introduced any complex numbers, but it's called double roots. So, you know, occasionally we talked about double roots, right? Where we have the the parabola just kissing the x-axis, just touching tangentially the x-axis, and we say there's two roots right on top of each other, right where it touches. Well, that's because in the quadratic formula, you have a square root of 0 here, so the two roots end up becoming the same thing, negative b over 2a. You technically have two of them, but they're the exact same thing, and that happens when the discriminant is equal to 0. So what I want you to do is keep this in the back of your mind. And the discriminant here, as we all know, we're going to write it down here, the discriminant is equal by definition to be b squared minus 4 times a times c. The square root is not part of the discriminant. It's just what's underneath the square root. That's what we talk about, what the discriminant really is. So there's three cases. If the discriminant's bigger than 0, we know that we have two roots. They're real roots and they're unequal because we have plus and minus, whatever's under that radical, or after you take the square root. If it's less than 0, we still have two roots, but they're complex conjugates because we have negative numbers under the square roots. If the discriminant's actually equal to 0 perfectly, then we've added and subtracting 0, so we have exactly the same roots 2 times over, so we call it a real roots because there's no i's involved and it's a double root. Now what I want to do now is I could just leave it here and say let's solve some problems, but I really think it's instructive to go look at what happens. So let's go over to the computer and take a look at what happens when we look at the discriminant of different kinds of quadratic equations. Okay, welcome back. In this case, we have what we have here in this demo here is initially we have x squared, which is a parabola that you all know and love, but with these sliders here, I can actually change what this parabola looks like. And what we're going to do over here is take a look at, this is the quadratic formula, negative b plus or minus square root b squared minus 4ac over 2a. But here I've calculated the discriminant, which is now we calculate to be 0. So that was that very special case. Remember, when the discriminant's equal to 0, the roots here, which are also being calculated, is the double root located at 0, which is exactly what the graph shows, because this parabola kisses and just touches the x-axis here right at x is equal to 0. So notice if you calculate this discriminant, b squared minus 4ac, a is going to be 1 because it's 1x squared, b is 0, and c is 0. So b squared minus 4ac, when you work it out, b squared would be 0 minus 4 times a times c is 0 in this equation. So it's basically the discriminant 0, and that's what we have here. Now let's take a look at a couple of different cases. Let's make the discriminant positive. We can do that easily by shifting this graph up, right? So we have x squared plus 1. Now the discriminant is actually negative. Let's go ahead and I actually went the wrong way. Let's go and first make it positive. Let's go down this direction. And you can see that what's going on here is now the equation is x squared minus 2. If you calculate b squared minus 4ac, it'll be negative 8 because b is 0, so it's 0 minus, and then you have 4 times a times c, 4 times 1 here times negative 2, and the minus sign here, negative times negative is positive, you actually get a positive discriminant for this case. So because you have a positive discriminant, that's the case when you have two real roots. In this case, you see the roots are calculated, negative 1.4, positive 1.4. And so when the discriminant is positive, we get the two real roots, which are separated like this. Now I can change this equation slightly. Now this is a very slightly different one, but you can see again, the discriminant is positive and we get two real roots. I can flip it around, make it a little more narrow. We still have two crossing points. We still have two real roots here. There's no imaginary numbers involved. The discriminant is positive. So no matter how I actually jockey this thing around, I can bring it over on this side. I can change it, make it more like this. Let me shift it up a little bit, something like this. The discriminant again is positive. And then I see that I have the two real roots. So the way I want you to burn it in your mind is anytime this discriminant turns out to be positive, the graph crosses the x-axis in two locations, and then you have the two roots which are calculated here. Now let's go and see what happens when the discriminant's negative. So I can shift this graph up and take a look at what's going on in this parabola right here. I have x squared minus 4x plus 5. Now when you work through that b squared minus 4ac discriminant, you're going to get a negative 4, which means when I take the square root of the negative number, I'm going to introduce imaginary numbers. So now my two roots are actually imaginary. So this covers the case when the discriminant's negative, you get the two imaginary or two complex roots which are conjugates of one another. Notice the 2 and the 1i and 2 plus 1i, 2 minus 1i. It's exactly the same thing, differing only by a sign. And I can move this guy. Let me try to keep it upstairs up here. I can move this all over the place. Let me see if I can shift it over, like right over on this side of the graph here. You can see I still have a negative 4 for a discriminant. I still have complex conjugate roots. Now, interestingly, I can change this let me go ahead and try to move it back to where I started here just so you can kind of see what goes on. When I change this to larger and larger numbers, it gets narrow, but I can go the other direction. So let me go ahead and make this guy negative and bring it down like this so that you have an upside down parabola like this. There's still two crossing points. I still have a positive discriminant. When you work out b squared minus 4ac is still positive, and because of that, I have my two real roots. I can move this upside down parabola wherever I want to, as long as my discriminant is positive, which you can see it is positive in all of these cases. I have my two roots, which are real. But as soon as I grab this guy and bring it down below the axis so I don't have any actual real crossing points, the discriminant turns negative. When you work out b squared minus 4ac here, you're going to get that negative discriminant, and whenever that happens, no matter where I shift this thing, when it's underneath the axis and I have that negative discriminant, I'm going to get these complex conjugate roots. So that's what I want you to understand. When the discriminant's positive, you get real roots, and when the discriminant's negative, you get these complex conjugate roots. Now what we need to do is talk about the very special case when the discriminant is equal to 0. So let me flip this back around and bring it back to where we started this thing from, because that's the best way to start here. And we had that very special case with the quadratic y is equal to x squared when the discriminant actually already equals 0. And that was the third case. When we had the discriminant equals 0, we talked about on the board how that gives us basically two identical roots. In this case, they're both centered here at x is equal to 0. Now I want to dial in a couple of different equations with double roots. So let's do x squared. Let's do minus 2x plus 1. I've already figured these out ahead of time. So here's another quadratic equation. You can see the graph goes down and touches the axis in only one location, so we expect a double root right here at x is equal to 1. So we have two roots, x is equal to 1, identical roots, and the discriminant for this is 0. So if you dial in b squared minus 4ac and calculate it, you're going to get a 0. That's why we have the double roots located here. Let me show you one more. We'll do negative 4x squared plus 12x. Let's see if I can get all the way to 12x like this. Whoops, we've got to go up a little bit more to 12x. And then we're going to go minus 9. I've already looked at this ahead of time, so I know exactly where to go. It's kind of hard to find them randomly. But if you run b squared minus 4ac through this discriminant here, a being negative 4, b being 12, and c being negative 9, then you'll get a discriminant exactly at 0, and you'll see that you have a double root here exactly at 1.5, two roots in the same location. So the bottom line, most important thing for you to understand in all of this stuff, the only reason I even put this together is I really like visual things when I can do it without too much work. And I think it's really, really nice for you to see that when these quadratic graphs cross the x-axis in two locations, then we have two real roots, and you can see them here. And no matter where I move this thing, wherever I shift it, as long as I have two real crossing points, I'm going to have the two real roots and the discriminant will be positive. But as soon as this graph pops up above where there's no crossing points on the x-axis, then at that point the discriminant always turns negative and I don't have any real roots anymore because I don't have any real crossing points. I have these imaginary or complex conjugate roots. And then of course you have the very special case, which we just looked at a minute ago, of basically whenever you don't have, let me go and get it over here. When you don't have two distinct crossing points, you have basically the graph just touches tangentially the axis. The simplest case is y is equal to x squared. In that case, the discriminant's not positive, the discriminant's not negative, but in the case of double roots, the discriminant turns out to exactly be right in the middle of those at 0. In that case, we have two roots. And in fact, you can see the roots here. The roots are really far apart. Negative 2.2, positive 2.2. And as we get closer and closer, the roots get closer and closer together, closer and closer together, closer and closer together. Finally, the roots are exactly on top of each other. We have two of them. And then now we don't even have any real roots at all. They're just complex numbers. And we're going to talk more about that a little bit later. So for now, I'm going to close this section out and we're going to work some problems in the next lesson where we talk about this a little bit more concretely. All right, so now that we have done the computer work, we have solidified what we wanted to talk about, which is how the discriminant predicts what the roots will look like. If the discriminant's positive, we're going to have two roots which are real. We saw that many times over. If the discriminant's negative, we're going to have two roots which are complex and they're conjugates of each other. If the discriminant is exactly equal to 0, then we're going to have a double root where the graph is just touching the x-axis in one location really, but it counts 2 times, and that's what we get in the case of a real double root. Now there's one more thing I want to show you before we go on and do the problems in the next lesson, and that is kind of like something that's still related to the discriminant, but I wanted to save it for the end. It just makes a little more sense to put it there after the demo. What I want to talk to you about is what happens if what is under here, the discriminant here, what happens if it's a perfect square? In other words, we can take the square root of 13. Of course, we have a decimal answer, but the square root of 13 is an infinite decimal. It's not, you can't really take the decimal value of it unless you truncate it. The square root of 2, the square root of 3, they go on and on forever when you convert to decimals. So, but some square roots are perfect squares, like square root of 36. We know that that's 6 exactly. Square root of 49 is 7. We know that that's exactly the case. We know that the square root of 100 is 10. We know that some of these things we call perfect squares. When we have a perfect square that lives under there, taking the square root produces a lot more simple answer. We don't have any radicals in those answers. So let's talk about the case when we have a perfect square under there. So first let me say if we have two conditions. The first condition is we have integral coefficients of my quadratic equation. In other words, A and B and C they're not decimals, they're not fractions, they're just whole numbers, negative or positive. That's what an integral coefficient means. Also, it means we could transform our original quadratic equation by multiplication or something into something with the integral coefficients. The other constraint is, let's see what happens if this discriminant is equal to a perfect square, which is rare actually because there's only so many perfect squares. I mean, 4 is a perfect square, 9 is a perfect square, 16, 25, you can go up 36 and so on. Those are the special ones where you can take the square root and you get just a whole number back, right? Very special numbers. So if you have a quadratic equation with integral coefficients, and if the discriminant is one of these very, very special perfect numbers, like 25, 36, and things like that, then what you're going to have when you calculate this thing, the solutions, is going to be negative b plus or minus the square root of this perfect square, all divided by 2a. So b squared minus 4ac is just a perfect number like 36 or 100 or 49 or something like that, but not a perfect square of those very special numbers. All other numbers are not what we consider perfect squares. So if you have a perfect square that lives under here, then what you're going to get as an answer is going to be rational roots. Roots. Remember the word rational? We talked about that before. The word rational just means you can write it as a fraction. So in other words, if no matter what b is and a is, if what is under here is a perfect square, like let's say it's 36, I'll take the square root, it'll give me a 6. Then negative b plus 6 over 2a, if a, b, and c are all integral coefficients, you see, then what if my radical basically disappears because I can take the square root of it and get that number back, then no matter what I'm adding or subtracting or dividing by, it will be rational. The answer will be rational because it will be a fraction. In other words, there'll be no radicals in the answer. So for instance, to contrast it, if I put 13 under the radical, then it would be negative b, whatever that is, plus the square root of 13 over 2a, whatever a is. I cannot get rid of that square root of 13. 13 is irrational. It goes on and on and on forever as a decimal when you try to convert it to a decimal. So the last part of this lesson is just telling you that, hey, there's certain constraints on D that tell us a lot about the solutions. If it's positive, we have 2 roots that are real. If it's negative, we have 2 roots that are complex. If it's 0, we have 2 roots that are real and also what we call a double root. And on top of that, if what is under here is a very special number, like 36 or 49 or 100 or 9 or 16 or something like that, then when you do all the math here, you're always going to get a rational answer, like 1/2 or 1/3 or 22, meaning you could write it as a fraction, 22 over 1. No radicals in the final answer because I've gotten rid of my square root when I have that perfect square there. But if I have something other than a perfect square there, like 20, well, I can't get rid of that square root. Square root of 20, I can do a factor tree, but I'm still going to have a radical left, so the answer will not be rational. So sometimes on your test, you might say, hey, here's an equation, don't use the quadratic formula, but just calculate the discriminant and tell me if the answers are going to be rational or not. All you have to do is say, well, what's under this radical? Is it a perfect square or not? And that'll tell you if it is a perfect square, you're going to get rational answers, meaning you can have no radicals in your answers. So make sure you understand this. Follow me on to the next lesson. We're going to use everything we've learned here in order to actually solve some problems involving the discriminant. Learn anything at mathandscience.com.